Multi-cylinder radial engine. The present invention is directed to the internal combustion engine, particularly to a two-cycle multi-cylinder internal combustion engine, boasting a common crankcase and a firing order. In a radial configuration of the engine cycles, the firing order is in sequence 1, 2, 3, 4, and so on, according to the number of cylinders used. In the inline V or opposed configurations, the firing order is determined by the position of respective throws on the crankshaft. The engine is on a type started by applying a voltage from the internal source to glow plugs, and the applied voltage is removed when the engine is started. If a spark ignites, used to ignition must remain on. A typical two-stroke engine is one in which each complete rotation of the rotatable crankshaft corresponds to two-stroke, one forward, one back, of a reciprocating piston connected to the crankshaft with a connecting rod. With the power stroke for every complete rotation of the crankshaft, a simple four-stroke engine also employs a piston and a connecting rod to rotate a crankshaft, but there is only one power stroke for every two complete rotation of the crankshaft. For the same size or weight, the two-stroke engine generates a higher power output than a four-stroke engine and is therefore sometimes preferred. A multi-four-stroke engine may have plurality of cylinders in line and a V arrangement opposed or in a radial arrays relative to the common crankshaft axis. Each cylinder and piston arrangement requires respective intake and exhaust valve and associated shared crankshaft or the light to operate the valve in specific sequences. A single carburetor is typically employed, especially for small engines, to provide a controlled mixture of air, fuel, and oil to the cylinder. Lubrication for the moving part and a four-stroke engine is typically provided by blow-by residual oil in the cylinder, which passes by the piston into the crankcase, or via sump providing oil for internal combustion in the radial configuration. When the engine stops, the lower cylinder collects the oil from the crankcase. This requires the removal of the lower plugs to prevent fouling for the plug and hydrostatic lock. A two-stroke engine, by construct, typically has only one cylinder driving one rotatable crankshaft substantially encased within a crankcase. A mixture of vaporizing fuel, air, and lubricant in the form of very fine droplets is contained in the crankcase under pressure produced by the piston travel downward into the crankcase. During the downstroke, the piston passes the exhaust port, expelling the exhaust to the previous cycle. The piston, upon traveling further downward a very short distance, exposes a bulbous intake port. The pressurized fuel, air, oil mixture passes from the crankcase into the top of the cylinder, replacing the exhaust gas, which continues to pass out to the exhaust port. On the second upstroke, the piston passes the intake and exhaust ports, sealing them for the crankcase. A vacuum is thus created in the crankcase, whilst simultaneously a pressure is being created at the top of the cylinder. Fresh air-fuel mixture enters the crankcase through a carburetor and the piston reaches the top dead center or TDC. An ignition source fires the compressed air-fuel mixture, generating a power stroke during which compressed products of combustion force the piston to make a working or power stroke. The connecting rod and the connecting crankshaft thus are moved into their respective power producing motion. Although it is possible to have two cycle cylinder assemblies and a single crankcase, both piston must reach top dead center at the same time and must also travel downward at the same time in order to create the pressure and vacuum necessary to operate the engine. This need to continuously generate vacuum to draw fuel, air, lubricant mixture into the crankcase and generate compression needed to charge the cylinder is why multi-cylinder two-cycle engine with a firing array, where each cylinder fires independently and alternately of the other, are not known. It is well known in the mechanical engineering arts that the two-stroke engine has fewer parts, needs little or no maintenance, and provide a higher power to weight ratio than does the comparably sized four-stroke engine. Cooling system. A system which controls the engine temperature is known as a cooling system. An internal combustion engine is a heat machine that converts chemical energy in the fuel into mechanical energy at the crankshaft. It does not do this without some loss of energy. However, and even the most efficient aircraft engine may waste 60 to 70% of the original energy in the fuel, unless most of this waste heat is rapidly removed. The cylinder may become hot enough to cause complete engine failure. Excessive heat is undesirable in any internal combustion engine for three principal reasons. It affects the behavior of the combustion of the fuel air charge. It weakens the shorten the life of an engine part. It impairs lubrication. If the temperature inside the engine cylinder is too great, the fuel-air mixture is preheated, and combustion occurs before the desired time. Since premature combustion causes denotation, knocking, and other undesirable conditions, there must be a way to eliminate heat before it causes damage. 1 gallon of aviation gasoline has enough heat value to boil 75 gallons of water. Thus, it is easy to see that the engine that burns 4 gallons of fuel per minute releases a tremendous amount of heat. About 1/4 of the heat released is charged into useful power. The remaining of the heat must be dissipated so that it is not destructive to the engine. In the typical aircraft power plant, half of the heat gassed out with the exhaust and the other is absorbed by the engine. Circulating oil pick up part of this suck in heat and transfer it to the airstream through the oil cooler. The engine cooling system takes care to the rest. Cooling is matter to transferring the excess heat from the cylinder to the air, but there is more to such a job just placing the cylinder in the airstream. A cylinder of the large engine is roughly the size of the gallon jar. An outer surface, however, in the increase by the use of cooling pins so that it presents a barrel size interiors the cooling air. Such an arrangement increases the heat transfer by radiation if too much of the cooling pin area is broken off. The cylinder cannot cool properly and a hot spring develops. Therefore, cylinders are normally replaced if a specified number of square inches of pins are missing. And the cooling system serves three important functions. First, it removes excess heat from the engine. Second, it maintains the engine operation temperature where it works most efficiently. And finally, it brings the engine up to the right operation temperature as quickly as possible.
Welcome to Auto Tech Labs. Let's see how a car engine cooling system works. A car engine is basically an internal combustion engine where power is generated through expansion of high temperature and high pressure gases. A lot of heat is generated due to the combustion gas and the friction of mechanical parts. For sustained operation, these excess heat should be removed from the engine and kept at operating temperature. Now let's see the parts involved in cooling the engine. The main parts for cooling the engine are water pump, radiator, thermostat, coolant temperature sensor, and coolant. First, the water pump. Water pump is the heart of the cooling system, which pumps the coolant. It consists of an impeller, a pulley flange, and an O-ring. The impeller is driven by the engine drive belt through a pulley. Next, the radiator. The radiator is a heat exchanger used to transfer the excess heat developed by engine to the atmosphere. The radiator is having an inlet port, outlet port, a drain plug, and a radiator pressure cap. The radiator pressure cap plays a vital role in the cooling system, which will be explained later. Next, the thermostat. The thermostat is a valve which regulates the flow of the coolant and helps to maintain the proper operating temperature for the engine. The thermostat consists of a frame, charge cylinder, main valve, main spring, bypass valve, and secondary spring. Next, the coolant temperature sensor. The coolant temperature sensor is used to monitor the engine temperature. The ECU will use this data to manage fuel injection and ignition time. Some engines have more than one coolant temperature sensor. The data is also used to control the radiator fan and to update the temperature gauge on the driver console. The coolant temperature sensor consists of a sensing probe and an electrical connector. Most coolant temperature sensors are negative temperature coefficient type, which means as the temperature increases, the resistance will decrease. The CTS can be a 2-pin type, or a 3-pin type, depending on the make of the vehicle. These are the main parts involved in an engine cooling system. Now, let's see how these parts works together. The pistons are contained inside the engine block, in which each of them will function. Above the engine block comes the head gasket, which provides sealing between engine block and engine head. It avoids compression leaks and oil or coolant leaks into the cylinders. Above that comes the engine head. The engine is having a safe passage, through which the coolant can flow without entering into the cylinder, or mixing up with the oil. This passage is known as water jacket. Let's put the parts one by one, and see how it works. The water pump pumps the coolant throughout the system with the help of the radial impeller. It is driven by the engine itself, using a serpentine belt. The serpentine belt also drives the power steering pump, alternator, AC compressor. But for now only water pump is shown. Now let's see the connections. The thermostat bypass hose. The thermostat housing. Inside the thermostat, the radiator, and the radiator fan. The lower radiator hose. The water pump outlet hose. The upper radiator hose. The coolant expansion tank. The expansion bleed hose. Coolant overflow hose. So, finally, let's get into the working, starting with the thermostat. The thermostat is actually a valve, which regulates the flow of the coolant. It will always be covered in the coolant, so that the temperature can be sensed. Let's start the operation from a cold engine. When the engine is cold, the bypass valve stays open. So, the coolant bypasses the radiator and recirculates through the engine. This helps the engine to heat up to operating temperature quickly. Eventually, the coolant temperature increases by absorbing the heat from the engine. Once the coolant starts to reach higher temperature, which is usually between 160 to 190 Fahrenheit, the bypass valve will start to close, and the main valve will start to open. This allows the cold coolant from radiator flow to the engine side, and the hot coolant from engine side flow to the radiator. In most cars, the coolant temperature sensor is located near the thermostat housing. It will turn on the radiator fan if the coolant to the radiator side is at high temperature. Now, the hot coolant in the radiator will release its heat to the atmosphere with the help of the fan. At the same time, the cold coolant received from the radiator will start to absorb the heat from the engine for the next cycle. Heating liquid inside a closed system always builds up pressure. So, how to maintain the pressure? Here comes the role of the radiator pressure cap. It consists of a spring-loaded valve mechanism, which will respond to higher pressure. Reaching a pressure above 15 psi will push the pressure cap valve, and the coolant flows to the expansion tank, until the pressure goes down to operation level. And when the system cools down, the vacuum inside the system sucks back the coolant from expansion tank. In case if there is too much pressure build-up in the system, due to trapped air, or other failures, the coolant in the expansion tank will be pushed out through the overflow hose. The car heater system is a part of the engine cooling system. The heater system comprises of the heater core, inlet and outlet hoses, a heater control valve which is optional and cannot be found in all vehicles. The heater core acts as a radiator, dissipating heat from the hot coolant to the vehicle interior, using a blower.